Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this tutorial video, I'll go through this 9701 Cambridge International A-Level exam. This is an older exam series before the introduction of the really big revamped syllabus in 2016. So this was just before that, and I will highlight whatever questions that are no longer relevant to the new syllabus as I go through this particular paper. This is paper 23, so it's paper 2 variant 3 for this June 2015 exam. In this first question, neon is a noble gas, so we need to complete the full electronic configuration of neon. These are the full configurations. As you go across the first row of the periodic table, you get 1s2, then you have to fill in the new shell. In the S block, there's lithium and beryllium, and then you will go to 2p6 because this is the sixth element in the P block. It actually has got 8 electrons in the outer shell. As you know from IGCSE, GCSE or O-level chemistry, 2-8, these are the IGCSE, GCSE and O-level configurations. These are the configuration we use in AS as well as A-level chemistry. In this second question, what is meant by the term first ionization energy? I know they don't ask you for an equation, but the thing that I usually teach my students is to write an equation first. So I'm just going to use X here. The gaseous atom of X will lose 1 mole of electrons, and you will get X plus cations. This is gaseous cations. By writing this equation, you will be able to define it as the energy required. So first ionization energy is the energy required because to remove electrons from what it is attracted to, which is the nucleus which contains the protons, is going to take energy. It's going to be endothermic always. It's the energy required to remove 1 mole of electrons. We focus on 1 mole instead of 1 electron because this thing has a unit of kilojoule per mole. Per mole of what? Per mole of electrons being removed. And you are removing from what? From 1 mole of gaseous atom. So if you look on the left hand side of the equation, you have 1 mole of gaseous atom and you're removing it from 1 mole of gaseous atom. So this is usually your second point. And what is your third point? What are you forming? To form 1 mole of gaseous ions. I know different textbooks that will have different sort of definitions. I'm just going to run you with my definition first. Gaseous ion with a +1 charge. So this is the same thing I do with all my other topical playlists, as you will see with the rest of my channel. So I see 3 points here. Like I said, different textbooks will use different definitions. They can say 1 mole of gaseous monocation, which means single cation. They can talk about singly positively charged gaseous ions. I simply choose to use a simpler language, easier to understand. Gaseous ions, it is gaseous, it is ions, it has a +1 charge. That's it. I mean, I'm just defining based on the equation and there's nothing wrong with it. And you cannot fault an answer like this as well as any sort of answers from a textbook. They all mean the same thing only. Explain why the first ionization energy of neon is greater than that of fluorine. We know that in general, our first ionization energy trend, in general, they increase across a period. This is across a second period. We know it will increase, drop slightly as you go to the P subshell, drop slightly again as you have paired electron repulsions, and then it goes all the way up to neon before you fill in the new shell, and therefore it will drop all the way down there. So there's lithium, and we know this is group 2 to group 13, so beryllium and borons. We know there's going to be nitrogen and oxygen where you have paired electron repulsion, and here you have the electrons filling the P subshell, which is further and more shielded compared to these valence electrons in the S subshell. But this question is not asking you on those specific drops. They're asking you on fluorine versus neon. Fluorine versus neon. So from fluorine to neon, what actually happened? Okay, there are 2 marks to this. So we have to talk about essentially why the first ionization energy increases from fluorine to neon. So from fluorine to neon, we can talk about the number of protons. So I should really use full words instead of abbreviation. That was what I was used to. Number of proton increases. So the number of protons will give you your nuclear charge. So your nuclear charge would also increase. And as the nuclear charge increase, what can we say about shielding? Shielding will be roughly constant, so approximately constant, meaning they are not changing. And that's simply because the electrons are filling in the same shell and the same subshell there. So the valence electrons are filling in the same shell. The valence electrons fill in the same shell. That's why there is not much shielding difference there. Overall, the net electrostatic force of attraction, the net electrostatic force of attraction, well, essentially the effective nuclear charge, that's why it's called the net electrostatic force of attraction. This is between the protons in the nucleus and the valence electrons would be stronger. Stronger for neons, therefore more difficult to remove. Higher first ionization energy, therefore higher first ionization energy. Straight to the point there, in terms of shielding be the same or similarly constant, but the nuclear charge increasing, the overall net effect called the effective nuclear charge will get stronger for neon compared to fluorine, and therefore they are much harder to remove. The new syllabus also mentions something about size as well. You could also say that as a result of this stronger net force of attraction, neon will be smaller in size than fluorine, although that is not actually true. If you have the actual data booklet, you will see that neon is actually bigger in size than fluorine, just like argon is actually bigger than chlorine, but you're no longer given the data booklet in the new A-level chemistry exam, so there's no way you will know something like that. So that's why I avoided talking about the size. I just talk about the net force of attraction there. The next question, neon has 3 stable isotopes. Your job is to find what is the missing mass number here. We don't know this number here. It's a whole number based on this, 2021. We don't know whether it's bigger than 21 or smaller than 20. We really don't know. But what we know is it's not the most abundant. The most abundant one is isotope 20. So it makes sense that your relative atomic mass, which is defined as the average mass. This is defined as the average mass of all the isotopes. And this is relative to the atomic mass unit, which is defined as relative to 1/12 times the mass of one atom of carbon-12 isotope. Okay, so what is important there is that this is average mass, whereas the isotopic mass are these specific mass which are not average for the individual isotopes compared to 1/12 the mass of an atom of carbon-12 isotope. Now we gotta use the relative atomic mass of neon, 20.2. It's very close to 20 because isotope 20 is abundant in close to 90% there. So we know the relative atomic mass is equal to the mass number times the percentage abundance. So 9.25 times x plus 90.48 times 20, and then 0.27 times 21. The whole thing added up together, and you will get out of 100%, as these are percentage abundance there. As I move up the 100 from the bottom to the top there, so what I get is I get 20.2 times 100, and I just get 9.25x. I get 90.48 times 20 plus 0.27 times 21. I will get 1815.27. Of course, then I just need to move my whole number to the other side. 20.2 times 100 is 2020 minus 1815.27. My x is going to be that thing minus that, and I get 204.73 divided by 9.25, and I get 22.13. Of course, then they don't tell us how many decimal place, but then we look at the data provided. This will in whole number for the mass number, so I'm gonna round this up to the nearest whole number just to be consistent with the data given. The next question, this looks like ideal guess questions because you have a mixture of neon and argon. You want to find the average MR of the mixture. So we get PV equal to nRT, but we know that the N stands for the number of mole, so that is mass over MRRT. So to rearrange that, MR is going to go up, and then the PV is going to come down, so it's going to get MRT over PV. So when I get all of that, so what I get is the mass, well, the average mass, the mass combined for both gases there, 0.275 gram. My R will be given in the data booklet, although they are not separate now. They'll be given at the end of your paper 2 booklet, of course. So 8.31 joule per Kelvin per mole, or joule per Kelvin per mole. The temperature must be in Kelvin. So 25 degrees Celsius convert to Kelvin, you have to add 273. This adds up to 298 Kelvin. Now our pressure is 100 kilopascal. So kilopascal have to be converted to Pascal. So now I have 10 to the 5 Pascal. So it'll be 1 times 10 to the 5, something like that. And last but not least, we have our volume given in cm cube. This is one of the trickiest one. But 1 cm to convert to meter is 1 divided by 100. And you can represent this in terms of indices. So 1 divided by 100 is 10 to the minus 2. What I'm going to do is I cube both sides. This is usually my favorite method because I do not need to memorize any conversion factor apart from my primary school conversion factor, change cm to meter, divide by 100. I also know how to cube both sides. 1 cube is 1, cm cube is cm cube, 10 to the minus 2 cube is 10 to the minus 6, and this is meter cube there. So overall, what I get is I convert my volume from cm cube to meter cube, by multiplying by 10 to the minus 6 meter cube. I'm not going to write all of this again because I've just spent some time writing this value on the side. What I do now is I just press my calculator based on what I have written down, and that's perfectly okay because everything is laid out perfectly like that, rather than me wasting my time and doing all over again. So I've done the top bit. I'm going to divide by, oh no, I've done the top bit but I accidentally clear it. Just give me a minute. So okay, and then divide by 10 to the 5 divided by 200 times 10 to the minus 6. Make sure you know how to press this on a calculator. 200 and then exp, that means times 10, and then you press minus 6, and then there should be 200 times 10 to the minus 6. I get the MR of 15.01. They don't talk to us, they don't tell us about how many significant figure, but looking at the data, like the mass 1, 2, and 3, 1, 2, and 3, I can think of this as 3, I can think of this as 3, or can think of them as one significant figure. I'm going to leave my final answer to 3 significant figure, just to be consistent there with the data given. So the unit of MR is actually going to be gram per mole. This 15.0, well, it's okay, I guess, because neon has a relative atomic mass of around 20. I wonder if I've done anything wrong. Let me just double check my calculation. 25 plus 273 is 298. Okay, I better check my calculation. This seems a bit low. Perhaps I made a mistake. 31 times 298 divided by that, divided by that. There you go. I know I've made a mistake because, if you think about the relative atomic mass of neon, that is going to be around 20.1. So, how can my average MR be lower than that when argon is heavier than that, okay? But these are just intuitions, and I've done chemistry for a longer period of time than you as a student, I guess. So perhaps that was why I could spot this kind of inconsistency. Since I made a mistake once, I'm just going to double check my calculation again because, if I can't make that mistake, you can possibly make that mistake as well. Not saying that you will, but there's that potential that you might make that mistake as well. So just keep an eye out for this kind of stuff, yeah? Now the next thing, what is the percentage of neon in the mixture? Use your answer to 1. What is the percentage of neon in the mixture? So let the percentage of neon be X, let's say. And then we know the relative atomic mass of neon was 20.2. So that's 20.2 from the previous question. Therefore, the percentage of argon will be equal to 100 minus X because you have neon and argon. So if this is 100 minus X percent, and do we know the AR of argon? Yes, we do from the periodic table. 39.9. 39.9. So what we can say is 20.2 multiplied by X plus 39.9 multiplied by 100 minus X divided by 100. That is going to give us 34.1. I am not sure if I'm going on the right way. So I'm talking about like the average mass. When I combine these two together based on the percentage present, it's going to give me this average MR. So based on that, I'm going to move up the 100 to the top. I'm going to get 3410. And I can evaluate the left hand side. 20.2x plus 20.2x, that is not going to look right. 39.9 times 100, that is 3990. So I have just expanded the bracket there. And then I have minus 39.9 plus 20.2. So 20.2 minus 39.9, that is minus 19. 0.7x. And I can do this calculation, I guess. So 3990 minus 3410 is equal to 19.7x. So x is going to be the percentage of neon. So that's 580 over 19.7. There could be an easier way. I don't know whether I've done the wrong way or not. So this is 29.4%. This is the 3 significant figure. So give or take, you can see that the 34.1 is much closer to the argon, which is a bit heavier, rather than closer to the neon, which is a bit lighter. That's because you probably have a lot more argon compared to neon, and that shows because around 30% of this lighter one and 70% of the heavier one. Okay. On to the next question. So neon and argon can both be obtained by fractional distillation of liquid air, just like we could get liquid nitrogen, or we could separate nitrogen and oxygen from the air by using fractional distillation because they have different boiling point. So this neon is a noble gas that exists as single atom. So both of them exist as single atom. Name the force that need to be overcome to boil, and explain what causes it. So we are looking at something called van der Waals forces. In the new syllabus, in the 2022 new syllabus, they have changed these to have been renamed. Not really renamed, they just added a few things. You can call them London dispersion forces, or instantaneous dipoles, or temporary dipoles. They all mean roughly the same thing. Explain what causes it. So there are electrons inside the atom. So we're talking about the monoatomic or monatomic noble gases, and then this induces temporary dipoles. Those delta plus delta minus on the neighboring or nearby molecules, nearby atoms on the neighboring or nearby atoms, and hence the temporary dipole name, which is also known as London dispersion forces or van der Waals forces, which arises as a result of electrons inside the structure, inside the molecule, inside the atom. In these cases, they are not static. The electrons are always moving, and as they move around, they can create or induce temporary dipoles on the neighboring or nearby atoms. Last but not least, you also have argon. Argon has a higher boiling point than neon. That is a result of argon has greater total number of electrons. You will see that there are 2 marks. So greater total number of electrons in the atoms. So the van der Waals is stronger. But that is factor number 1. There is also a second factor, which is to do with surface area. Argon has bigger size because it has 1 more shell. So 1 extra filled electron shell, as it is further down in the group 8 or group 18 in the noble gases group, and this is compared to neon. Therefore, bigger surface area due to the bigger size. And both of these factors result in overall argon has stronger van der Waals or stronger London dispersion forces between the atom. Stronger London dispersion forces, or you can talk about van der Waals, slightly more energy to overcome. Or to break, and therefore, it has slightly higher boiling point compared to the other simple monoatomic structure, which is also true for both noble gases. It just comes down to which one has a greater total number of electrons, as well as which one has a bigger surface area. And that's the end of the 80-mark question there. In this second question, so we have some group 2 chemistry. So started out by talking about magnesium, calcium, barium. By the way, the new syllabus will have replaced this Roman numeral by these by this numeral type rather than this Roman numeral in the new syllabus. So describe and explain the trend in reactivity of these three elements with cold water. So you gotta describe and explain. Well, first of all, we're gonna describe the trend. So the group 2 metals become more reactive with water. So they become more reactive with water, with cold water down the group. In fact, so what we know is magnesium has no reaction with cold water. In fact, magnesium does not react with cold water. Magnesium needs to react only with steam and it will form magnesium oxide. Okay, so does not react with cold water. So what happened there is we need to talk about down the group, down group 2. So the valence electrons are further away from the nucleus because we involve losing the electrons in a redox reactions. So the valence electrons being further away from the nucleus because they are more filled electronic shell. Since they are more filled electron shells, they are also more shielded. So we can talk about shielding also increases. So overall, we can talk about it's much easier to lose them. Overall, weaker net electrostatic attraction of the valence electrons to the nucleus. And if they are less attracted to the nucleus, easier to be lost. And that is how group 2 metal will react. They lose the outer shell electrons. If easier to be lost, they become more reactive going down the group 2. Okay. Anyway, it is saying that magnesium does react with cold water in this case, even though we know that it will react extremely slowly and you need really like steam in order for magnesium to react at a considerable rate. Magnesium can react with cold water but extremely slowly, but they do want an equation. So we're going to write this formation of magnesium hydroxide, and that equation is not balanced actually. Because it will release hydrogen gas as well, because metal plus water, metal hydroxide and hydrogen gas. This is with water and not with steam, so that's why it's hydrogen gas. Although this is a very slow reaction, you probably don't see any effervescence or whatnot. We need to balance our equation no matter what. We have to balance this with 2H2O, that is 4 hydrogen. 2 hydrogen plus 2 hydrogen is 4 hydrogen, 2 oxygen there. So this equation is nice and balanced now. Suggests why the water eventually turns cloudy during these reactions, because magnesium hydroxide is not very soluble in water. So it's not very soluble in water because your group 2 hydroxide only increase in solubility going down group 2. So this is not very soluble in water. Therefore, it will precipitate out in a large amount. As you continuously produce it, it will precipitate out. Now suggest the equation for the reaction of hot magnesium with steam. This one has got a high activation, not high activation energy. It's got a fast rate of reaction. That means the activation energy is much lower compared to with the cold water. Magnesium plus steam, they are not asking for stat symbols, but they already specify that it's with steam. You do not get magnesium hydroxide, because even though magnesium hydroxide is not very soluble in water, you do not have water, you have steam here. So it's not water, so they don't dissolve in it. And if you think about it, the other product will be just the hydrogen, just to balance the equation there. The next bit, the oxides of magnesium, calcium and barium all can react with dilute nitric acid, and that is because the oxides of group 2, so group 2 oxides, they are all basic oxide. So we know from our 14 to 16 years old O level, GCSE as well as IGCSE level chemistry, basic oxides can react with acidic oxide, or they can also react with acid. In this case, you have magnesium oxide, Mg2 plus or 2 minus. So in a 1-to-1 ratio, you have H plus NO3 minus nitric acid. Your salt is going to be magnesium nitrate. So Mg2 plus NO3 minus. The 2 and the 1, they are the valency based on the charges of the ion. When you do the LCM, lowest common multiple, that is called how many of the ions do you need? Well, you need 1 Mg2 plus, you need 2 of the NO3 minus, based on the exchange of this valency, which is based on the principle of lowest common multiple, primary school mathematics. The formula of magnesium nitrate, there is 1 Mg2 plus, there are 2 NO3 there, and I will produce water, neutralization reaction between a basic oxide and an acid. I have 2 of that nitrate, which can only come from 2 of that nitric acid unit. So 2 NO3 minus give me the 2 NO3 minus, the 2 hydrogen there combined with 1 oxygen to give me 1 water there. Every equation written in this Cambridge exam has to be balanced. The next one, just state the trend in the thermal stability, how stable it is to heat. So down group 2, in fact this is no longer the Roman numeral, so down group 2, the nitrates become more stable to heat, and therefore they want thermal stability, so I have to specify the thermal stability of the nitrates would increase. They become more stable to heat, so it increase in stability. How about when you do decompose one of it, magnesium nitrate further up in the group 2 nitrate, so it does decompose fairly easily compared to the bottom of the group 2 nitrate. That will give you the group 2 oxide, Mg2 plus O2 minus 1:1 ratio. You get this brown gas, NO2 gas, you get O2 gas produced as well, and you will get 2 NO2 because you got 2 NO3 minus there, so 2 NO2. Now balancing the equation, 2 times 3 is 6 oxygen atom, so 6 oxygen atoms. What you get there is 1 oxygen, and what you get there is 2 NO2 molecule, so there is 4 oxygen atoms. That means if you want to balance the equation, we just need 1 oxygen atom there, and it's always been my favorite to use fraction, so 1/2 times 2, which we can't change the identity of the molecule. Half times 2 is 1 oxygen atom, 1 plus 4 plus 1, 6 oxygen atom. Some people really don't like the half. I don't know how or why. In AS level standard, if you still don't like the half, you're not going to do well for the enthalpy topic when there's a lot of fraction involved. But if you really don't like the half, you can multiply the whole thing by 2. You get 2, 2, 4, and 1 there, and you'll still get the exact same answer, which will be correct, which will be 1 mark. The next bit of the question, apart from lithium nitrate, the nitrates of group 1 elements decompose in a different way. So the lithium nitrate behave similarly to the nitrates of group 2 elements. So this is potassium nitrate, so it behaves differently from the group 2 nitrates. By identifying any changes in oxidation number, explain which element is reduced and which element is oxidized. Well, if we look at KNO3, when we look at oxidation number, we just look at one particular unit. So the potassium there is K plus 1 because this is potassium nitrate. Potassium in a compound is going to be K plus. So therefore, we are looking at NO3 minus. So we're looking at nitrogen plus 3 times minus 2 equal to minus 1. Oxidation number of the ions is going to be the charge of the ions. Nitrogen is what you have to find. Oxygen in these compounds is going to be oxygen minus 2. So there are 3 of them, 3 times minus 2 there. Nitrogen is minus 1 plus 6, which is plus 5 there. So nitrate is going to be nitrogen plus 5. Very, very straightforward there. And the next bit is on KNO2. So KNO2, again, K plus 1 in K plus. So what we have is NO2 minus. In NO2 minus, what do we have? We have N and then 2 oxygen. 2 times minus 2 is minus 1. Nitrogen is minus 1 plus 4. Nitrogen is plus 3 there. And last but not least, we have oxygen O2. We have O2. This is just oxygen 0 in O2. So altogether, what we can see here really is, I'm just going to remove those things there, and then I'm just going to move some of these around. Let me see. That thing there is the nitrate. So the nitrate is going to the nitrite. The NO3 minus is going to the NO2 minus. Let me just create some space there. And then you're also forming the oxygen like that. So what we can see is we have oxygen minus 2 in KNO3. We have nitrogen plus 5 in KNO3. So this one, the oxygen minus 2 is going to oxygen 0 in O2. And this nitrogen plus 5 is going to nitrogen plus 3 in KNO2. This is an increase from minus 2 to 0. That is something you would call oxidation, increase in oxidation number. And the next one, plus 5 going to plus 3. This is a decrease in oxidation number. This is called reduction there. Okay. This next question is basically asking us, in terms of structure and bonding, why does it have very high melting point? For that 2 marks, we need to mention that MgO, Mg2 plus O2 minus, has a giant ionic lattice structure. So giant ionic lattice structure or giant ionic structure. And what do we need to break when we melt MgO? Because of the giant ionic structure, we need to break the strong ionic bond. And this strong ionic bond is between oppositely charged ions, which in this case is between the Mg2 plus and the O2 minus ions, being very specific to the question that they are asking there. The next one, we're going to write equations. This is plural. And we're going to show how calcium carbonate can be converted into calcium hydroxide by a two-step process. What you know about group 2 carbonate is that it can thermally decompose under heat to give you calcium oxide, Ca2 plus O2 minus. You will get CO2. And what happened with this calcium oxide is you can dissolve calcium oxide in water, and then you will get calcium hydroxide, as that's what they're required there. They want equations. You need to give balance equations. These are the two balance equations there. Now this last bit is asking you to write an ionic equation. So in an ionic equation, you must have stat symbols. This is between hydrogen ion and carbonate ion. The H plus ion is present in acid. The carbonate ion is present in metal carbonate. So you're talking about any carbonate will react with acid. That is the test for carbonate, as you will know it from paper 3 practical studies, and also from your previous practical or alternative to practical back then in qualitative analysis topic. You will get carbon dioxide produced as an effervescence. You will also get water molecule. If you think about balancing the equation, there are 2 hydrogen there, so we need 2 H plus, and the plus 1 times 2 cancel out the minus 2 times 1. Plus 2 minus 2, no charge overall on the left, no charge in molecules overall on the right. They haven't asked for stat symbols. It's always been my standard usually to write in a stat symbol for ionic equations. So we're talking about aqueous acid, because acid is dissolved in water to give you H plus ion. And then we have carbonate, which we are assuming is aqueous in this case, but we are not told whether it's aqueous or solid. And here we definitely have liquid water and gaseous carbon dioxide there. I'm sure you won't get penalized if you don't have the units. It's only 1 mark anyway. But you must have a balanced equation. Now the very last bit of this question, use your equation to calculate the mass of powdered calcium carbonate to be added to neutralize the acidity. You will see that the H plus acidity, the concentration is 1 times 10 to the minus 4. You have this much total volume. So the first thing you can do is you can find the mole of the acid, which we know N equal to CV, where C is mole per dm cube, and then V is volume of solution, and this is volume of solution in dm cube, because mole per dm cube must be multiplied by dm cube for the unit to cancel out. So what I normally do is to compare the mole ratio directly. So we want mole of calcium carbonate. 1 calcium carbonate will give you 1 CO3 2 minus, and this is relative to the H plus. So 1 of the calcium carbonate reacts with 2 of the H plus. On the right hand side, we want the mass of the calcium carbonate. If we want the mass of the calcium carbonate, it's important that we have the MR of the calcium carbonate. So going to your periodic table, you will have calcium, which is 40.1, plus 1 carbon, 12.0, plus 16.0 times 3, I get, hang on, 40.0 plus 12.0 plus 16.0 times 3, I get 100.1. So that is mass of the calcium carbonate divided by the MR, which is 100.1. This thing on the right hand side is the mole of the calcium carbonate. The one at the bottom has to be the mole of the H plus. This is the concentration in mole per dm cube. This is the volume already in dm cube. So I don't need to convert anything into dm cube again, because that was conveniently already mole per dm cube times the volume already in dm cube there. So I just need to move this up there. When I move the bottom to the left hand side, I do not change anything on the half. So it's just bring up the denominator, and this is equal to mass of calcium carbonate divided by 100.1. I'm going to do this in one go. I will move up the 100.1 to the other side, and the whole thing will be multiplied by 100.1. So if I move this up there, this is multiplied by that, and I can just now press my calculator. 100.1 times 0.5, which is 1 over 2, times 1 times 10 to the power minus 4 times 8,000, I would get the mass of the calcium carbonate to be 40.04. This is going to be in gram, as this is gram over gram per mole. But then looking at the data, this was given to, like, you can think of this as 4 or 1 significant figure. This is also 1 significant figure. I don't think I should give to too many significant figure. Maybe 1 or 2 should be all right. If I give it to 40 gram, you can interpret this as 2 significant figure or 1 significant figure, which is all right given the value, the data that we have been given in this question here. And that's the end of that 19 marks. Pretty long question there. Question number 3, this is the beginning of the organic structured questions. So we are told that there are 6 molecules. They are all structural isomers. Structural isomers defined as molecules which have the same molecular formula but different structural formula for obvious reasons. C4H8O, 4 carbon, 8 hydrogen, and 1 oxygen. A, B, and C give you orange precipitate with 2,4-DNPH. So A, B, and C has ketones or aldehyde. So they will give you a positive orange precipitate when they condense, when they undergo condensation with these 2,4-DNPH. Only A and B give a brick red PPT, so only A and B are going to be aldehyde, because only the aldehyde can react with phalanx or toluenes. When it reacts with phalanx, which is blue solution, you'll get a brick red PPT. This brick red PPT is copper plus 1. You're going to get copper 1 oxide. That is going to be Cu plus and O2 minus. So you're going to have 2 of that Cu plus. So that thing there is Cu2O, copper 1 oxide there. And what do they want? They want skeletal formula, my favorite of all time. There are 4 carbons. So we're looking at 4 carbon aldehyde and 4 carbon aldehyde. And there's no other information given. If we look at aldehyde, aldehyde has to be CHO, so aldehyde must be at the very end. If they don't give us information, I will just draw the simplest aldehyde, straight chain 4 carbons. So this thing is going to be CH3, CH2, CH2, CHO. Carbon form 4 bond. If I only show 1 bond to carbon, there are 3 more hydrogen which are not shown. Carbon form 4 bond, 1, 2, so there are 2 hydrogen. Carbon form 4 bond, 1, 2, so there are 2 hydrogen. Carbon from 4 bond, 1, 2, 3, there's 1 hydrogen there. This is structural, this is skeletal. They want skeletal, we are not given the choice, we must draw skeletal. Now onto the other ones. This is a straight chained aldehyde, but of course you can see there are 3 carbon here, then you can branch out. This is very typical. When you have 3 carbons, you can branch out. Now you can have 1, 2, and 3. So this is now propanol, and this is 2-methyl propanol. This is going to be CH3, CH, bracket CH3, CHO. So that's the name there. We are not asked for the name, obviously, but you know, it's quite interesting if you think about what sort of things could be asked, obviously. And this first one there, they didn't ask for the name, but it's a 4-carbon aldehyde. This is just butanol. On to C, this one is ketonaldehyde, but they it doesn't give you the brick red PPT, it doesn't give you the positive result with the Fellings reagent. So this must be a ketone. And we're looking at 4 carbon ketones, C4H8O. These are isomers. These are functional group isomer. Ketone and aldehydes have the same molecular formula, but different functional group here because they are functional group isomer, specifically coming under structural isomer. So 1, 2, 3, 4. You can of course draw the other way around, which is this way around. This is also 1, 2, 3, 4. Both of them will have the same name. It's called butanones. You can name it butane 2-on, but there is only one isomer. Butane 2-on is butanone. Now name the type of structural isomers shown by A and B. They didn't specify which one is A, which one is B, because they didn't mention which one is branch, which one is straight chain. This is very clearly open to interpretation. You could have gotten, B as the straight chain or A as the branch chain. It doesn't matter because there's no other information to tell us what is A or B apart from 4-carbonaldehyde. And the relationship between the straight chain and the branch chain is called chain isomerism. It comes under structural isomerism. Just like the relationship of A with C or B with C is functional group isomerism, aldehyde ketones. Now state what you would see, describe what you would see when A is 1 with Tollens. Tollens reagent is basically silver plus 1, but it's got 2 ammonia. So it's a soluble complex, and we'll learn more about complex ions in A2 transition metals. So this is aqueous, this is colorless solution, If A contains aldehyde, aldehyde can be oxidized by Tollens, and then this silver plus 1 will go to silver 0, and you will see a silver mirror or silver precipitate forming. So typically the best result that you will see is a silver mirror. You will see a silver mirror forming, but sometimes you can get like a gray precipitate or a gray solid forming. There's also a result of the silver atoms getting produced or getting formed without forming the silver mirror, because experimental issues, sometimes you don't get a perfect silver mirror. Now we're talking about 4 carbon just now. I think C4H8, C4H8O. So when we look at C4H8O, we are not looking at aldehyde or ketones. So these are D, E, and F. They are not aldehyde, not ketones, because they did not give you the orange PPT with 2,4-D and pH. But they all decolorize bromine. If they all decolorize bromine, they must have carbon-carbon double bond. This is called test for unsaturation. Unsaturated stuff, they will add bromine onto the double bond, and therefore you will get decolorization of the bromine water from orange or from yellow-orange to colorless. Effervescence slowly with sodium metal. So this is with sodium metal, which is a reactive metal, and there is OH group. So are we sure that it could be carboxylic acid? Yes, but it could also be alcohol, because alcohol can react with sodium as well to give you hydrogen gas. Carboxylic acid can react with sodium to give you hydrogen gas as well. And what do we know? E shows geometric isomerisms. Geometric isomerism is your cis and trans. Only D has a branch chain. None of these isomers, none of them contain a oxygen atom bonded to a carbon atom involved in pi bond. So we are saying that we do not have this, nothing like this, none of these. So we have a carbon involved in pi bond, but we do not have any oxygen atom bonded to a carbon involved in this carbon-carbon double bond, which is a pi bond, 1 pi and 1 sigma bond there. None of these isomers contain a chiral center, none. So no chiral center, remember, no chiral center. Give the structures of D, E, and F, and you got to show the 2 stereoisomers. If you want to show the stereoisomers, you cannot use structural isomer, because if you define stereoisomer, they have the same molecular formula, they have the same structural formula. So you cannot use structural formula to show the difference between cis and trans. It doesn't work. Must display at the carbon-carbon double bond to show the cis and the trans, and then of course label the stereoisomerism. What do we need? So we have 5 marks here. Let's try and draw this. So there are 4 carbons. D. If I just draw my double bond, and then is this doable? So there is 1, 2, 3, and 4. So there are 4 carbons. Hydrogen 1, 2, 3, 4, 5, 6, 7, 8. And then there is no oxygen. There is no oxygen directly bonded to that. But then D has a branch chain. So I can't branch it unless I remove this one and branch it there. So only then I can branch it. So perhaps I have this thing here like this, and then I just branch it there. So this is my branch chain. But I now have an issue because you see this is chiral. You see how this one has a carbon bonded to CH3, OH, something with double bond, and then a hydrogen. So this cannot be the answer. This one is this one there. So, you know, cannot be. Cannot have a chiral center. Cannot be. So cannot be that answer. I wonder what else could it be. 4 carbons. 4 carbons. And only E has cis and trans. So I'm okay here. How about this one? Wonder if this is alright. This is straight chain, so this is not branch. So let me see. If I have branch like this. So this one has no branch. So this one cannot be the answer. Because this one is straight chained and you're looking for branch. I cannot have cis and trans, so this is a CH2. Both groups are the same on 1 carbon of the carbon-carbon double bond, so no geometric isomers for D. It has a branch chain, so this is the branch. There is no oxygen bonded to a carbon atom, which are, you know, involved in pi bond, so this is bonded on the next carbon. There is OH, so it does react with sodium metal, and I think D must be this one then. Okay. As for E and E, we are looking for the cis and trans isomer. So we cannot have this. We cannot have this, all right? Because there is no oxygen directly bonded to a carbon involved in the carbon-carbon double bond like that. So we must be looking at cis and trans like this, perhaps. 1, 2, 3, 4. And then we are missing an OH. And the OH cannot be directly bonded to the carbon with a double bond. So it has to be bonded to the next carbon. I have drawn them to be the exact same thing because they are on the opposite side. So this is called the trans isomer. The cis isomer is not this one. I have to change this slightly. And this one will be the cis isomer, where the CH3 is on the same side as the CH2OH. On to F. What do we know about F? F has carbon-carbon double bond. F could be this. No, F cannot be this because this one contains a chiral carbon. F does not have geometrical isomer. F must have OH group. F must have carbon-carbon double bond. I think F is possibly the straight chain. I think F is possibly this one because, you know, there is no chiral carbon. There is no branching here because they say only D has a branch chain and only D has a branch chain. There is no geometric isomer because only E shows geometric isomers. And then none of them contain chiral center, so it cannot be this, it must be this. Okay, hopefully that makes sense to you. When these alcohols react with sodium metal and you get this alkoxide. So this is a giant ionic structure. And then you will give H2 gas, hydrogen molecule. But of course, you only have 1 hydrogen atom to give away. So we must balance our equation no matter what. Identify the gas. It's going to be hydrogen gas. Or you can write down H2 gas because they don't say about name or formula. But they did say if you write down the hydrogen gas, you have to write down H2 instead of hydrogen atoms. Now part C, this is about balancing equations. So we're going to use oxidizing agent is this square bracket O, which is counted as 1 oxygen atom, or this square bracket H for reducing agent, like sodium borohydride. So we're given these molecular formula which are easier to balance, to be honest. We're going to react it with acidified potassium dichromate 6. So this is the orange color reagent, chromium plus 6, which is orange. you're supposed to be able to work out the oxidation number. -2 is the overall charge of the ion, equal to 2 chromium plus 7 times -2. So 2 chromium is -2 plus 14. 2 chromium is plus 12. So each chromium is plus 6. And then this orange color will go to chromium 3 plus, which is chromium plus 3 green in color. That is the positive result if it does act as an oxidizing agent, because it oxidizes the alcohol here. Or is it alcohol? It's not alcohol actually. It says contain the same functional group as A. Contain the same functional group as A. What was A just now? A is aldehyde. So aldehyde can be oxidized to carboxylic acid. Aldehyde can be oxidized to carboxylic acid. So C3H6O, am I correct? So 3 carbons, 1, 2, and 3. CH3, CH2, CHO, 3, 4, 5, 6. So C3H6O. We're going to oxidize that. It's going to go to carboxylic acid. And then when it gets oxidized to carboxylic acid, we have CH3, CH2, CO2H, which is equal to 3 carbons, 3, 4, 5, 6 hydrogen, and O2. So C3H6O2. And this equation is balanced in terms of carbon. 6 hydrogen and 6 hydrogen, 1 oxygen plus 1 oxygen, 2 oxygen. This equation is balanced now. On to the next one, you have reducing agent. So the same thing, we're going to reduce aldehyde. And when we reduce aldehyde, we will get the primary alcohol. Running out of space there, but there's the primary alcohol. CH3, CH2, CH2OH. So there is a total of 3 carbons. And then 3, 4, 5, 6, 7, and 8 hydrogen and oxygen. So 6 hydrogen, 8 hydrogen. I need 2 hydrogen atoms in order to add up to 8 hydrogen. The oxygen and carbon are already balanced. And that's the end of that 13-mark organic question. Question 4. So we have this question here where we got alkene. And we also got alcohol here. The carbon with this OH is bonded to one other carbon. This is called primary alcohol. What are we looking at? What is the organic product? You're looking for organic product, something that contains carbon and also hydrogen and stuff. When you react with cold dilute acidified potassium manganate 7, this is the mild oxidation of alkene. And when you do mild oxidation of alkenes, you are just going to add OH and OH. You're going to form diol, where both carbons of the carbon-carbon double bond gain oxygen. So they say give the structure. They don't say skeletal. They don't say structural. You can follow this one. And you can just give, like where you lost a double bond, you give OH and OH. My usual favorite is to draw skeletal. So I'm going to convert this to skeletal. You don't have to follow my usual standards, but skeletal is beautiful and you are expected to be able to master skeletal in AS chemistry so that you have an easier time in A2. CH3, CH3 there, CH3, CH2OH is there. So when you add OH and OH there, you're going to lose the double bond, and then you get OH, and then you will get OH like that. Of course, if you want to use the partial structural kind of format, which is the same as the question above, so you're going to get that, and then you're going to get OH and OH. This is not display, obviously. I haven't displayed every single covalent bond, but these or these will be alright because they don't mention skeletal or structural or display that for that 1 mark. The next thing, when you had hot concentrated KMNO4 and you look at structures and products, this is plural because you're going to rupture. You're going to rupture this carbon-carbon double bond. So when I rupture it, this is an extreme oxidation. You think about the conditions. So it's going to break the carbon-carbon bond totally. And when we break it, we need to consider this group there. It's carbon and carbon, so this is called RCR dash, carbon double bond, and that will give you ketones. So that will give you the ketone, which is like that. I think I can draw better ketone than that. So there's the ketone there. So there's the original carbon of the carbon-carbon double bond become a carbon oxygen like that. This is also alkyl and alkyl, so both of them CR dash, you will get another ketone. However, this thing there is primary alcohol. Primary alcohol will be oxidized by these extreme oxidation conditions, the oxidizing agents, and hot and concentrated. What you will get is, you will get carboxylic acid. So what we get there is a ketone and carboxylic acid. I can draw this slightly better, I guess, but let me see if I can draw it just a bit better, just to show you the format. So this one and this one, product 1 and product 2 there. They say structures again. You're more than welcome to use these kind of structures if you wish to. I've just done skeletal because I could do my skeletal easily. The next bit of the question is basically about the electrophilic addition mechanism onto alkenes. And they just want you to complete this thing. They already given you the dipoles that was induced by being close to these rich in electron. The pi bond is rich in electrons. So from the alkene double bond, attacks the bromine with the delta plus, and then give away the electrons to the Br with the delta minus. And now I'm going to form CH2OH like this, CH3, CH3, CH3. I'm going to think about where my bromine is going to add. Actually, it doesn't matter where the bromine adds, but here is better, because if I add here, the carbon with the positive charge, which I have bolded here, is bonded to 1, 2, and 3 other carbon, is going to be tertiary carbocation. Tertiary carbocation is more stable than secondary, more stable than primary carbocation, because you've got 1, 2, and 3 alkyl electron donating groups that can stabilize the positive charge on the carbon. Now the Br minus with the lone pair on the Br minus will attack the carbon with the positive charge, and that will result in the formation of the final product J there. Explain the origin of dipole in the bromine molecule. So we know that bromine and bromine, they have equal electronegativity, so they are non-polar. So where is the dipole coming from? So the electrons in the pi bond, which are called the pi electrons in the alkene, that is rich in electrons, that will polarize and induce dipoles, delta plus and delta minus, on the nearby Br2 molecule. Okay, so it will induce the dipole. Perhaps I don't want to use the word polarize, I just say induce the dipole on the nearby Br2 molecules. Basically, it comes from the rich in electrons from the pi electron clouds above and below the carbon trigonoplanar plane, carbon sp2 trigonoplanar plane there. Now J is formed as an equimolar mixture of isomers, so 50% of each enantiomers. So enantiomers are those mirror images like your left and your right hand. They are non-superimposable. So this 50% of each enantiomer, they rotate clockwise as well as anti-clockwise in opposite directions. That's the only difference between the mirror images, because they have every property being the same. They rotate plane polarized light in opposite directions, and this optical activity will cancel out. And if this optical activity cancels out, even though you have a chiral carbon, but then it will be optically inactive. Overall, you don't see any rotations of plane polarized light, even though you have a chiral carbon. That is because of equimolar mixture of isomers, there is a specific term for these called racemic mixture. Racemic mixture, when you have 50% or equal mixture of each enantiomer. This type of isomerism, the one that we talk about optical activity, optical rotation, is a result of optical isomers, mirror images of each other that are non-superimposable. Draw the structures of the two isomers of J, and this happened to be the last bit of this question. We always have to draw up a mirror image. So we draw a mirror plane. We try to show our tetrahedral structure, two flat ones separated by roughly 109.5 degree tetrahedral geometry. So the flat one goes to the flat one, the one away from the mirror plane, and then you have this bolded one, and this bolded one is moving away from the plane as well, and then you have this dash one that move closer or towards the plane there. What do we have about J? J here, which ones are chiral carbons? This is CH3 and CH3, so this thing is not chiral because this group and this group are the same. groups. So it must be this carbon there. So if I just quickly sketch out BrCH3, CH2OH, and then CH3CH3Br, because it's a lot easier to think about in terms of skeletal formula. The two CH3, the Br, the CH2OH, and the CH3. It's probably easier when you have the paper next to you, but it's not that easy on the screen if I have to keep on looking back at it. So this is our chiral carbon, which I'll put an asterisk on. So what do I have there? I have a carbon. Well, I guess if I want, I can draw display formula if I want to. I'm not going to draw display actually. It's a bit scary. What do I have? I have a CH3, and a Br. So this thing there is the big group on this side. I have a Br, a CH3. I'm going to put the Br there because that's easy. I'm going to put the OH there and then the OH there. And last but not least, I wonder if I have made an easier choice. Doesn't matter. So I will have CH2 OH like that, or I can write CH2 OH. So you read backwards, so be careful. CH2 OH. If you don't like doing it this way, you can put the CH2 OH there somewhere and then you can display the other one properly. So this thing here, it does not matter where you put it because these things are single bonds and they can rotate about the single bonds. So whether the Br is there, but it's probably a lot easier to understand this being a mirror image when this Br goes to this Br there. As long as you show this being tetrahedral with two flat lines and then one coming out towards you, coming out from the plane, from the screen, and this away from the screen, and this projects the mirror image onto that, you will be fine with the two mirror images there. And of course, that is the chiral carbon. Usually we asterisk it to indicate or to show that it is the chiral carbon. And for that 2 marks, and that's how easy it is to get the 2 marks, hopefully for you. This is the end of that 10-mark question. This is the end of this whole paper actually. So thank you for watching, and don't forget to click the button on the bottom right to subscribe to my channel, and do follow me at ptet.chemistry. That's at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram. And do share the channel widely with other friends who can watch all the topical playlists for free. And if they feel it's worth it, they can get all the yearly paper tutorials by upgrading to the silver tier membership, either via VPN or direct subscription to the silver tier membership. Thank you for watching. Thank you for supporting the channel. I'll see you in the next tutorial video.